the late 1950s, NASA has been perfecting how to land spacecraft on planetary bodies. So it's probably fair to say we know everything we need to know about that science, right?
Well, not quite. Although missions from the past have been very successful, today NASA researchers are working on new technologies to improve the science of entry, descent, and landing. Hey, I'm Johnny Alonzo.
And I'm Jennifer Pulley. And today on NASA 360, we'll find out how NASA's new Hiad project is helping reinvent ballistic entry, descent, and landing, and why this is so important for future space missions. Before we jump into NASA's new Hiad project, let's first take a few minutes to talk about how we've been getting spacecraft into planetary atmospheres for over the past 70 years. The average person probably doesn't spend much time thinking about how spacecraft land on other planets, or even how they land back here on Earth. But let me tell you, it is extremely challenging to get this process right. Long before humans were sending spacecraft to other planets, we were, of course, learning how to do it back here in the Earth's atmosphere.
Apollo 11, this is Hornet, over.
In the early days, our first atmospheric entry tests used ballistic missiles that featured long nose cones with very narrow tips. These missiles had relatively low drag when entering the atmosphere at high speeds, which means that they would cut through the air easily. But the low drag and high speed of the missiles often led to excessive heating, which commonly melted the surface of the rockets. This problem confounded engineers for years. But in the early 1950s, NASA researchers Harry Allen and A.J. Eggers Jr. came up with a seemingly counterintuitive approach to solve the problem. Instead of using the thin, sleek missiles, they began testing blunt nose reentry vehicles. They demonstrated that a blunt body with its greater drag would have a detached shockwave. This detached shockwave transferred far less heat to the vehicle than the traditional shapes did. In layman's terms, the air cannot get out of the way quickly enough and acts like a cushion that pushes the heated shock layer away from the vehicle. Now, since most of the hot gases are no longer in direct contact with the vehicle, the heat energy would stay in the shocked gas and simply move around the vehicle and dissipate into the atmosphere. Now, this theory was a breakthrough, leading to the designs of the Mercury, Gemini, and Apollo space capsules.
No doubt that the blunt body design worked well in Earth's thick atmosphere. But researchers and engineers had to change things up when it came to landing craft on planetary bodies with less atmosphere, like Mars, for instance. Why? Well, the Martian atmosphere is thin, about 1/100th of the atmospheric density of Earth. So as a result, when we send a mission to Mars, the Martian atmosphere does not create a huge amount of drag on a vehicle as it would back here on Earth. We need all the room that we can get to slow the vehicle down to make a safe landing. On a typical Mars mission, a craft will enter the Martian atmosphere traveling at over 15,000 miles an hour. Past missions have used innovative techniques like parachutes, retro rockets, and even airbags to slow vehicles down. But these are still not enough to land where we want on Mars. In fact, every previous Mars mission has landed below sea level because the vehicle could not slow down fast enough to land at higher altitudes. You can see the obvious problem. If you can only land below sea level, then what happens if you want to study, say, a high ridge that is well above sea level? With current technology, we can't really do it. And we haven't even mentioned that the physical size of the spacecraft drastically limits what can be put inside of it. Scientists and researchers would love to put lots of instruments on every Mars mission, but they can only fit a relatively small amount of instruments into the launch vehicle. So, what can be done? Luckily, researchers at NASA are rethinking how entry, descent, and landing systems should work and have come up with a promising new design called the Hypersonic Inflatable Aerodynamic Decelerator, or Hiad. I spoke with Dr. Neil Cheatwood here at NASA Langley to give us an overview of what Hiad is and what we can expect in the future. Okay, so talk to us about the Hiad project and how will implementing structures like these change the way we go to Mars?
What Hiad does, Hiad stands for Hypersonic Inflatable Aerodynamic Decelerator.
Okay.
When we go to other planets with an atmosphere, we actually use that atmosphere to slow us down with an aeroshell or aerodynamic decelerator. But we're currently limited by the size of that aeroshell. We can't go bigger than the launch vehicle shroud. The idea is to deploy something bigger than the launch vehicle shroud. So that deployable in this case is an inflatable, so that's the IAD. The hypersonic piece means we're deploying it outside the atmosphere, but it has to then handle the heat pulse of entry. When I say hypersonic, that's because that's when you're going really fast. So supersonic you've probably heard of. That's
Yes.
faster than the speed of sound.
Right.
Hypersonic, you're actually going more than 5 times the speed of sound, and often 10 or 20 times the speed of sound. And what that means is now you're going so fast, the particles are actually flying apart. You know, the molecules are breaking up. You've got a lot of energy there that ends up imparting a heat pulse to your vehicle. So this larger vehicle allows us to decelerate at higher altitudes so that we see less heating, so the materials we're making it out of can survive. We can land more weight at the same altitude that we can now, or we could land that same weight at a higher altitude on Mars, as an example. The Hiad can be used at any planet with an atmosphere, so we really think this is a technology that helps us with access to space, helps us with space exploration of the robotic variety and of human scale. And it's really a method to take what we currently have as far as launch vehicles and get more stuff to the destinations and do more science.
Okay, Neil, we have flown to Mars many times. Now, I want you to explain to us some of the challenges of sending a craft to Mars, specifically how it relates to the design of the aeroshell, stowing mission hardware, and how to get the craft safely on the ground.
Okay, so when we go to a planet with an atmosphere, we like to make use of that atmosphere. When we landed on the moon back in the Apollo days, we used just rockets because the moon doesn't have an atmosphere. But when we go to Mars or Venus or any of these other planets, there's an atmosphere there that we like to make use of. We can just deploy a drag device and slow us down. We did that for the Apollo astronauts coming back from the moon. Coming to the Earth atmosphere, we deployed a parachute to slow us down the final part. The challenge is with Mars, it's what I call a poor excuse for an atmosphere. It really is very thin. It's like the equivalent of 100,000 feet at Earth. And so the challenge is to try to actually slow down in that atmosphere before you hit the surface. And there was a lot of work done on this back in the 60s and 70s in preparation for Project Viking. So they had a very large technology development program. Much of that was dedicated to that supersonic element. How do we deploy a supersonic parachute or a supersonic drag device of some sort so that we can get extra drag after the heat pulse, but before we actually land. When we go through the atmosphere and go through that heat pulse, we take out like 99% of the energy we've got through that heat pulse. But we still, at Mars, we have the challenge of, well, we're pretty close to the surface when we get done with that, what do we do? So at Mars, we build as big an aeroshell as we can, and then we fly that and we slow down as much as we can, as soon as we can, and then deploy that parachute. In the case of Mars Science Laboratory, we had what we call a rigid aeroshell, and it's constrained by the size of the launch vehicle. It's 4.5 meters, and we really can't go much bigger than that and fit inside the rockets we have. Now, what does that matter? Well, the more mass you have, the more stuff you have, the more it weighs, the larger the drag device you need to get to the same location.
Because it takes more to slow it down.
Exactly.
It's heavier.
Yes, so if you double the weight of what you're trying to take down, you need to double that drag area or you won't get to the same location. Also, if you say, actually I don't want to go to that location, I want to go higher in altitude, now the problem gets even harder. And so, it makes it even more of a challenge. So what we can do with these inflatables is inside that shroud, we can pack our hardware, the payload we have, but then we can, once we get rid of that launch vehicle shroud right before entry, we can deploy something bigger. So that lets us get that area up. Now you can deploy something like an umbrella, and that would be a mechanical type deployable. We're looking at those concepts as well, but we think the inflatable is the most scalable, where we can get the largest area ultimately if we wanted to take humans or something like that to Mars. If you then wanted to take that same mass that we took to the surface for MSL, if we want to take that same mass and now land on the southern part of Mars, which is where the highlands are, this is where they're seeing evidence of recent water activity, we could do that by just keeping that same rover, but make a larger aeroshell with these Hyads.
So where else could we see the Hiad project being used?
Basically, as I mentioned earlier, any place with an atmosphere. So if we wanted to go back to Titan, the Europeans did the Huygens probe at Titan recently. It was a piggyback on the Cassini mission. We could go back to Titan. It has a very thick atmosphere, very thick, fluffy atmosphere. We like that one. Venus, a very thick atmosphere. We have to deal with the sulfur dioxide, sulfuric acid clouds, but
oh well, no worries.
Minor thing. But we could do Venus, we could do the gas giants. And one of the other areas is access to space. We're always talking about low-cost access to space. You know, that's been the driver since the 70s, is how do we get more stuff to space at a cheaper price? Launch vehicle asset recovery is another area we would like to look at. If you could bring back the solar panels, the computers, the tanks, all these things, and reuse them, because most of these things can be used multiple times.
Neil, explain where the payload would go in this structure and how it all works. It's amazing.
Okay, we're actually what would be on the back side of the aeroshell. The vehicle would come in, pointing in first by design.
Right.
This is where our heat shield material is. So this is like the silicon carbide or the Nextel on this outer layer. And behind it are these bladders. But the payload goes right in the middle. And if you recall earlier, we were talking about the limits of the launch vehicle shroud. Well, now really our payload here, rather than this aeroshell, is what's limited by the launch vehicle shroud. So as long as this fits into our launch vehicle shroud, we can deploy something bigger later. And we have all this stowed up in front, and it launches this way under the nose cone. This is all stowed in here.
Yep.
And right before entry, it unfurls. We pop the nose cone and this unfurls, and then we reorient it, and it comes back in. If we were going to Mars, this would all stay stowed while we're going to Mars. Protect it from micrometeor damage and the elements and stuff like that. If we needed to, we could even heat it inside to keep it to a certain temperature. And then you deploy it right before entry. And so we think we can use this Hiad device to take us through the hypersonic entry, the heat pulse, and through supersonic deceleration, through the transonic regime, and take us down to subsonic speeds for a parachute deploy or retro rockets or whatever we use for the final descent.
And land where you want to land.
Yeah, land hopefully where we want to land, and potentially much higher altitude, because we're going to get to that subsonic condition if we want to at very high altitudes, or we can shrink down this aeroshell and let it get to that subsonic condition lower down in altitude.
Neil, thank you so much for all the information on Hiad.
Appreciate it.
Stick around in a few. Johnny's going to have some more information on the high-tech materials that are used to develop these Hiads. You're watching NASA 360. We'll be right back.
The inflatable structures idea really isn't new. No, NASA engineers from the past have thought about making the system work. But its major obstacle was trying to find materials to make it happen. Major steps have been taken in the past few years that have led to drastically improved materials that have proven to be effective in the cold vacuum of space, while also being able to take huge heat loads on entry. To help us better understand the different types of materials being developed for these Hiads, I spoke with Steve Hughes to find out more. Steve, let's talk about these materials for a second, all right? So how can some of this stuff keep payloads safe from massive heat of entry?
All right, well, first you have to figure out what that massive heat of entry is. So, and that's a combination of the mass of the payload and the diameter that's decelerating the payload. Okay. So we do a lot of calculations, figure out what those environments are, then we go out and start off by looking for materials that can survive those environments.
So, I mean, are these single layers, or do they have multiple layers?
Well, we have actually two distinct assemblies. What you see behind you is the inflatable structure, and that gives the aeroshell form, gives us the drag area, and survives the pressure load or the aerodynamic forces that are being applied. Okay. But that can't survive the heat of reentry, so we have to protect it with something, so we have a thermal protection system. You'll hear it referred to as TPS.
Sure.
It has an outer ply that survives the high heat of the flow of entry, and then it has an insulating ply that knocks that heat or the temperature from the outer surface down to something that the back surface can survive. And then it has a gas barrier which prevents the gas from being ingested or drawn through the fabric and through the insulator, and thereby bypassing the insulating layer.
Okay, cool. Well, I mean, you have a bunch of examples here. Let's talk about them.
All right, well we can start here. This is actually the IRB3 TPS nose. It is, outer fabric is a refractory cloth called BF20. It's a Nextel fabric.
Sure.
It is actually pink. The pink is a sizing. It's a material that's put on to keep the fibers from being torn up during the assembly process, during the weaving process. Okay. It burns off when it's first subjected to the heat of entry. Uh-huh. And then the underlying ply that we have right now for IRB3 is a material called 3350, Pyrogel 3350. This is an aerogel. Aerogel is a very, very low density glass that's been impregnated into a fibrous batten. It's somewhat flexible, and then behind that, an assembly of polyimide film with a Kevlar scrim embedded in between it to give it a little extra strength.
So, how is this different from, say, shuttle tiles or the types of materials that they used back in the 60s?
Shuttle tiles are insulating materials. They're very good insulators. Unfortunately, they're rigid. Part of the problem that we have right now is if we're sending a payload to Mars or some other planet, and it's a very massive payload, you're restricted to the entry diameter, the drag diameter is restricted to what can fit inside the launch shroud. What we've come up with is an inflatable structure that we deploy and we cover with a thermal protection system, and that allows us to accelerate a heavier payload. So when we deploy, we can't use a rigid thermal protection system.
Okay.
It's got to be able to pack down into basically a tight can. It's packed kind of like a parachute is, and then it's got to be able to deploy.
Well, this stuff's very strong, obviously.
Well, actually, the insulator is not very strong, and that is why we've included a Kevlar material inside the gas barrier. Now, the inner ply, the inflatable structure, it is incredibly strong. It's a Kevlar braid, so we braid these tubes up, and then we insert a silicone sheet rubber sleeve. That sheet rubber sleeve keeps the gas inside and tensions all of the Kevlar fibers, and then when you inflate that thing to about 12, 15 psi, and you come up and thump it, it sounds like you're hitting a piece of metal. So wow. It's pretty strong.
Okay, how can we use this back here on Earth?
As I mentioned, we went out and looked at the commercial materials to find things that fit our application. So we actually adapted some materials from the furnace industry. So these aren't materials that were made specifically for our application. Furnaces, they need door seals, they need drapes, they need all sorts of things that are flexible that can tolerate thousands of degrees C. So we went out and looked at materials and picked some that could do that. Found insulators. This insulation right here is a pipe insulation. We don't really need to adapt these. We're actually adapting commercial industry products to our needs.
Steve, this was wild, man. Thanks so much for having us here at the spacecraft assembly area.
Hey, no problem.
All right, man.
So we've seen some of the long-term plans for the Hiad project, but before these techniques can be used on a mission with hundreds of millions of dollars at stake, they need to be tested on a smaller scale in real-world conditions. That is what NASA researchers are doing now with the IRVI project, or the Inflatable Re-Entry Vehicle Experiment. They already have several tests under their belt and are now working on another IRVI project that will help them continue to learn how to perfect these types of inflatables. I spoke with my friend Mary Beth Wusk to find out about this program. Okay, Mary Beth, so we have heard what these future Hiad structures might look like, but obviously, before we fly them, we have to test the basic principles. So talk with us about how researchers begin testing these new technologies even before building a structure.
The concept, you have to make sure you understand the issue that you're trying to solve. And I think you heard from Neil and Steve earlier, the idea is we want to be able to land a mass on a destination that has an atmosphere. And then you want to look at what currently exists in technology today, and also what constraints are you dealing with by the launch vehicle or just the testing environment itself. It's expensive to do flight testing, so we want to do as much as we can on the ground. Sure. So we do multiple ground tests in different areas. And when you fly, you're in a relevant environment, but when you're on the ground, you can only simulate usually one or two of those variables at a time. So it's a combination of these things mapped together. And we come up with a design that we then move forward to take into a flight configuration.
Sounds like science, what's that, the scientific method?
Exactly. You come up, you research, you observe, you look at you come up with a hypothesis, and then you do the testing to support the hypothesis, and then you go and you do the flight test and you validate your results. In parallel with the hardware that we're building and the testing that we're doing, we're also modeling these activities, and we're taking those models and we're looking at what we predicted we would experience, and then we actually test, and when we see those results, both the ground test and the flight test. So we are validating our models through this whole process.
Okay, so once you have gotten your hypothesis and you've done your research, then you actually know what you want to do, and then you can actually begin building a structure. What was the first structure that you built?
Our first things that we built, what we spent most of our time with, was working with the materials in wind tunnel facilities where we test them at small scale, a duration of flights that we simulate the relevant environment as much as we can. The next step that we worked on was the inflatable structure. So the inflatable structure itself and the design that we're going forward with for the IRBI-3 mission is a little different than what we did for IRBI-2. And then the thermal protection system, which blankets over the air shell itself. We're doing both of these in parallel. We're doing testing on the thermal protection system, the materials, to make sure they can withstand the high temperature rates that we're going to experience. And they're also looking structurally at the inflatable article itself. So we built several full-scale models of the engineering, we call it our engineering development unit. We built 2 of these articles, which show the structure of the vehicle itself. And then we're doing smaller coupon testing of the thermal protection system where we take it into facilities to the high heat rates that we experience. Another example of some tests that we've done on the ground. This is a ballistic range test model. It's in a sabot. This whole thing is put into a gun that's shot down at Eglin Air Force Base.
In 5, 4, 3, 2, 1.
Okay, Mary Beth, explain to us what this is here. Now you're laughing. Why are you laughing?
Because it's not the most photogenic piece of hardware that we have in our stables. However, this is one of our engineering development units of the article itself. So this is actually the inflatable article, but it's been dissected. And the reason we dissected it is as we tested it, we did over 50 load tests. And the load test is the article is experiencing the loads that we would be experiencing during the flight. So it's a lot of wear and tear on the hardware. What we've done here is after we completed all of our testing, we then dissected the inflatable article itself. So these were the bladders, and they've been cut, and what we've done is there are cords inside the article, which we've done. We took those cords out and determined the strength and how well will they do during these flights.
You guys do lots and lots of testing.
Yes, we do.
That's why things take a long time.
It does. So we're taking advantage of the resources across the agency. We have people that are thermal analysis, structural analysis, aerodynamicists. We have fabrication that we're building. This hardware is being built in the United States. You know, it's exciting, the activities that the whole nation is pulling together to make this mission possible.
Well, good luck with IRBI-3. We look forward to seeing the results.
Thank you.
Thanks, Mary Beth. It was a pleasure. As you can see, the Hiad project is really redefining how we'll get our spacecraft onto other planets.
And even how we can use this technology back here on Earth.
That's all for now. We'll catch you next time on NASA 360. How we will get our spacecraft onto other planets.
Doc, we're trying to find material.
High-tech materials that are used in these Hiads. Sorry.
Researchers and engineers had to change things up when it came to landing craft on planetary bodies with less atmosphere. Back here on Earth, maybe?
And even how we use
Yeah, sorry, yeah, my bad. And even how they use technology back here on Earth.
And that's all for now. We'll catch you next time on NASA 360.
Perfect, okay. Put them up, sorry, put them up, there you go.